These are the answers to the Chapter 20 practice quiz, starting with the multiple choice questions. Number 1. Which of the following statements is true concerning the reaction shown above? Now for hydrogen peroxide, H2O2, we go back to Chapter 4 on this. On page 132, they say that in compounds called peroxides, the O2 2- ion gives each oxygen an oxidation number of -1. So hydrogen is +1 on both sides of the equation, so hydrogen is not changing at all. Oxygen is going from -1 to -2 in water, so oxygen is being reduced, but it's also going from -1 to 0 in oxygen gas, so it's being both oxidized and reduced. Correct answer is C. In number 2, we are given two half reactions, one for aluminum and one for silver, and we have to calculate the standard cell potential for this reaction. So looking at the first reaction involving aluminum, we're going to have to reverse that reaction to get the aluminum solid on the left and the aluminum ions on the right. The second reaction does not have to be reversed, but to get the electrons to cancel, we have to multiply it by 3. Now this does not change the value of the standard cell potential. So by reversing the first reaction, we go from negative to positive 1.66. The second reaction, we just multiplied by 3, but it's still the same potential, so 0.8. So A and B are incorrect. You're not going to multiply the voltage by 3 just because you multiply the half reaction by 3. Correct answer is D, 2.46 volts. Number 3 involves an electrolysis experiment where current is passed through a 1 molar aqueous solution of lithium chloride. They say that chlorine gas is observed as a product at the anode, so somehow chloride ions are being oxidized to chlorine gas. But what happens at the cathode? That's our question. Both of these cell potentials are negative, which means that electrical energy must be supplied from an outside source for the reaction to occur. But which one of those reactions occurs? Here on page 860, we have not an aqueous, but rather a molten sample of sodium chloride. And they talk about sodium being produced at the cathode. Now, it says, do we obtain the same products if we electrolyze the aqueous solution of a salt instead of the molten salt? Frequently, the answer is no, because water might be reduced to form hydrogen rather than sodium being reduced. Look at those two potentials, -2.71 for the reduction of sodium, but only -0.83 for the reduction of water to form hydrogen gas. So because the magnitude of those numbers, 0.83 is a smaller magnitude than 3.05, it's going to be easier to reduce water than it is to reduce lithium ions. So correct answer is that hydrogen is produced at the cathode because the magnitude of that reduction potential for the formation of hydrogen is smaller. Number 4, we have to decide whether nitrogen is oxidized or reduced. Let's take a look on page 132. This is back in Chapter 4, Rules for Assigning Oxidation Numbers. For an atom in its elemental form, the oxidation number is 0. For a monoatomic ion, the oxidation number is the charge on the ion. Fluorine is always -1 in all compounds. So we have nitrogen starting out as 0 in both of these reactions. To form magnesium nitride, the nitride ion has an oxidation number of -3. But in the NF3 compound, if fluorine is -1, that means that nitrogen has to be +3. So in reaction 1, we're going from 0 to -3, so it's reduced. But in reaction 2, we're going from 0 to +3, so it is oxidized. So the correct answer, D, nitrogen is oxidized in reaction 2 and reduced in reaction 1. All right, for these next 3 questions, we have a table of information. we have a galvanic cell X, Y, and Z, and those are constructed from two half cells. So in galvanic cell X, we have aluminum and copper. In galvanic cell Y, we have aluminum and iron. In galvanic cell Z, we have iron and copper. We know the standard potential for X and Y. We don't know the standard potential for Z. That's our first question. What is the standard potential for galvanic cell Z? Let's take a look at the two reactions for which the cell potential is known, and can we combine those two reactions together in such a way that we can figure this out? Well, if I reverse this equation to get the iron solid on the left and the iron 2+ ions on the right, that would be a good start. But then the other reaction, I'm going to go ahead and just leave it the way it is because I want copper ions on the left and I want copper solid on the right. So I flipped the second equation in this table. So now I have a voltage of negative 1.22. I want to add those two equations together. The aluminums will cancel out. I'm going to have 3 as my coefficient for all the species. Now when I divide by 3, that's not going to change the voltage. So positive 2.00, negative 1.22, add those together and I get 0.78, and that is my answer. Number 6. In galvanic cells Y and Z, which of the following takes place in half cell 3? So half cell 3 involves a strip of iron in a 1 molar solution of iron 2 nitrate. Well, the iron in galvanic cell Y is going from positive 2 to 0. So in that reaction, the iron is being reduced. In galvanic cell Z, iron is going from 0 to positive 2, so it's being oxidized. So reduced in cell Y, oxidized in cell Z. Correct answer is C. Question 7 is about changing from standard conditions to non-standard conditions. So we're changing the concentration of the iron from 1 molar to 5 molar. Is that going to have an effect on the voltage? Let's focus on the iron. In galvanic cell Y, we're increasing the concentration of a reactant. But in galvanic cell Z, we are increasing the concentration of a product. So in cell Y, since the iron is a reactant, when you increase the concentration of a reactant, Q becomes less than 1, the cell moves further away from equilibrium, and the voltage increases. But in cell Z, the iron is a product, so you're increasing the concentration of a product, Q becomes greater than 1, the cell moves closer toward equilibrium, and the voltage decreases. So voltage increases in cell Y, and voltage decreases in cell Z. Correct answer to number 7 is C. All right, in number 8 we have 4 half reactions, and we have to find the combination that produces the largest cell potential. Now all of these are reductions, so one of these half reactions must be reversed so we can have one reduction and one oxidation. Then we add the cell potentials together. So I'm going to start with reversing the zinc to go from negative 0.76 to positive 0.76. The other one I want to pick is the silver. I'm not going to reverse it, but I am going to multiply it by 2 to get the electrons to cancel out. This does not change the voltage, so I still have 0.8. But 0.76 plus 0.8 is 1.56. That is the largest cell potential I could get from this information. So correct answer is silver and zinc, which is B. Number 9, based on the information in the table, which of the following reactions is favored to occur? Let's calculate the cell potential for all 4 of these reactions. With part A, I've got chlorine on the left as Cl2, and I've got chloride on the right. That means the first half reaction was not reversed, so it's 1.36. But the third half reaction, Fe2+, that one has to be reversed, so I get a positive 0.44. So far, that one should be the one that's favored. Let's confirm that B, C, and D all have negative cell potentials. So for B, I would have to take the third half reaction and write it as is. I would have to reverse the bromine half reaction, so I get a negative 1.06. Negative 1.5 means that's not favored. And then when I do the math for reaction C, I get a positive 1.06 because I didn't reverse it, but then I get a negative 1.36 because I had to flip the other half reaction around. So as you can see from this math, reactions B, C, and D all have negative voltages. Only reaction A is favored, and that's the correct answer. All right, number 10, we are given an equilibrium constant, which is rather large, 4 times 10 to the 15th, and we have to decide about the signs of delta G and the cell potential. So on page 813, this is back in chapter 19, it said that if delta G is negative, then K should be greater than 1. The more negative delta G is, the larger K is. And in chapter 20, on page 847, a positive value of the voltage, the cell potential, and a negative value of the delta G both indicate a reaction that is favored or spontaneous. So, if we have a large value of K, then we'd want delta G to be negative and the cell potential to be positive. Correct answer is D. In number 11, we're doing an electrolysis calculation. We're starting with 1 gram of calcium. First, we're going to go from grams of calcium to moles of calcium using the periodic table. Then we're going to go from moles of calcium to moles of electrons. So because the charge on calcium is +2, there are 2 moles of electrons required for every 1 mole of calcium that's produced. Now we have to go from moles of electrons to coulombs, and we do that with the Faraday constant. Again, we can cross off choices C and D because the number 2 has to be on the top. So 96.45 coulombs per mole. The final conversion involves 12 amps. So 1 amp is a coulomb per second. That'd be 12 coulombs for every 1 second. So correct answer is B based on where the numbers fall. All right, the last multiple choice question. We have a voltaic cell with copper and silver. We can tell that the silver is being reduced, so that's the cathode, and the copper is being oxidized at the anode. Now they're adding hydrochloric acid to the cathode, and there's a reaction between silver ions and chloride ions to make a precipitate. So since silver, which happens to be a reactant, the concentration of silver is decreasing, so we're forming a solid precipitate, we're lowering the concentration of silver, we are decreasing the concentration of a reactant. This causes Q to become greater than 1. This brings the cell closer to equilibrium and the voltage decreases. So correct answer is C. All right, now on to the free response questions. Number 1, we have a galvanic cell involving copper and tin. We don't have any information about the voltages, but we can take a look at the fact that as current flows through the cell, the mass of the copper electrode increases and the mass of the zinc electrode decreases. So at which electrode is oxidation occurring? Well, the observation is that the mass of the tin electrode is decreasing. Therefore, tin atoms must be forming aqueous tin ions. And that process is oxidation. So oxidation is occurring at the tin electrode. All right, in part B, it says, as the mass of the tin electrode decreases, where does the mass go? So we're losing mass because the atoms on the tin electrode are entering the solution as aqueous tin 2+ ions. All right, in part C, we have an expanded view of the center portion of the salt bridge, and we're supposed to label what's happening in the salt bridge. Remember that ions are traveling through the salt bridge. We have the cathode on the left, and we have the anode on the right. So the potassium ions, the cations, are traveling toward the cathode, and the nitrate ions, the anions, are traveling toward the anode. So that's what they were looking for. In my official answer key from the College Board, it says that the response should show at least one K+ ion moving toward the copper compartment on the left, and at least one NO3- nitrate ion moving in the opposite direction. Typical errors on this question by students where they gave incorrect formulas for potassium and nitrate, often dissociating them as neutral species, depicting free electrons in the salt bridge and showing various forms of tin or copper. A large fraction of responses included no reference to potassium nitrate at all. So if they didn't have the charge on the ions, they lost the point here. And some people were not quite clear exactly what the salt bridge diagram was doing. So hopefully you got this question correct by having cations go toward the cathode on the left and anions going toward the anode on the right. All right, this next question in part D. A non-standard cell is made by replacing the 1 molar solutions of copper nitrate and tin nitrate with the 0.5 molar solutions of these same compounds. So is the cell potential less than, greater than, or equal to? Well, the answer is that the cell potential is equal to that of the standard cell because the concentration of copper and tin has changed, but the ratio of tin divided by copper, Q, is still equal to 1. So the cell potential is the same as in the standard cell. Now we have to decide if this standard and non-standard cell are going to have different amounts of time to power an electronic device. The non-standard cell, although it has the same cell potential, it would power the device for a shorter time because we're starting with a concentration of copper of 0.5 molar. The supply of copper 2+ ions will be exhausted more quickly than in the standard cell where the concentration of copper was 1 molar. So this non-standard cell is going to reach equilibrium, where E equals 0, more quickly because there are fewer copper ions. So we're going to be running out of copper ions more quickly. All right, part E, we have 4 half reactions, and we have to pick which 2 half reactions are relevant to this reaction, placing a new tin electrode in a fresh solution of copper nitrate. We want tin with an oxidation state of 0, and we want copper with an oxidation state of +2. So let's use this equation that has solid tin, but reverse it. Let's use this equation because it has copper 2+ ions. So we're going to write the copper 2+ on the left, so we're not going to change that reaction at all. We're going to flip the tin half reaction, so the electrons will cancel out, and we have an overall cell potential of 0.48 volts. Justify that the reaction is thermodynamically favorable. Because we have a positive cell potential, the reaction is favorable. So the correct answer is copper 2+ plus tin 0 to produce copper 0 and tin 2+. Again, the reaction is favorable because the cell potential is positive. For the delta G calculation, we use the following equation. The N is going to represent the number of moles of electrons. That's 2. We have the Faraday constant, and we have the voltage of 0.48. Multiply coulombs times volts, and we get joules. So we get, unrounded, negative 92,626 joules per mole. Rounded off to 2 sig figs, we get either negative 93,000 joules per mole of reaction or negative 93 kilojoules per mole of reaction. All right, our next question involves this setup. It is a metal air cell. It's a type of portable energy, and we have an alkaline electrolyte paste, and we have a porous cathode membrane that lets in oxygen from the air. We have 4 half reactions. We know that the overall reaction involves zinc plus oxygen to make zinc oxide. So our first question is going to be involving the cell potential. Let's use the zinc oxide, but reverse it and double it to get that zinc oxide, ZnO, on the right with a coefficient of 2. Let's use this equation as is so we can get oxygen on the left. So if we add those 2 equations together, we get 0.34 volts and positive 1.31 volts. The electrons cancel out, and we have the overall reaction that gives us a cell potential of 1.65 volts. Now we have to draw an arrow on the diagram for the direction of the migration of hydroxide ions. Hydroxide ions are anions. Anions always flow toward the anode. So in this diagram, we have to show an arrow where the direction of the ions are traveling. The anions are traveling toward the anode. Common mistakes on this question would be students that drew an arrow along the external circuit. Some offered vertical arrows or pointed them up or down or both, or drew a double-headed arrow. But the correct answer is an arrow pointing toward the left, toward the anode. So we have this particular air cell. It's placed on a balance before being placed in use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? Now think about this. We're getting oxygen from the air. So a reactant is coming into this air cell from outside. The mass of the cell increases because as the reaction proceeds, oxygen gas from the air reacts with zinc in the cell, producing zinc oxide, which has more mass than the original zinc. The zinc air cell is taken up to the top of a mountain where the air pressure is lower. Will the cell potential be higher, lower, or the same? The cell potential is going to be lower under these new conditions. So at the top of a mountain, the partial pressure of oxygen, which happens to be a reactant, will be less. So we have a lower concentration, if you will, a lower amount of reactant molecules. So the value of Q is going to increase, and it's going to take us closer toward equilibrium. The cell potential will be lower than the standard cell potential because we are decreasing the amount of reactant. So Q increases and the voltage decreases. All right, these metal air cells need to be lightweight, so let's take a look at sodium versus calcium as potential anodes. If we have 1 gram of sodium and 1 gram of calcium, which one is going to transfer more electrons? A common mistake would be to forget that sodium and calcium actually have different numbers for their moles of electrons. You can't just convert from grams to moles and compare the moles of sodium and calcium. You have to compare the moles of electrons, and notice that calcium supplies 2 moles of electrons for every 1 mole of calcium, whereas sodium has 1 mole of electron for 1 mole of sodium. So the correct answer for the metal that is able to, as an anode, transfer more electrons is calcium. 0.05 moles of electrons is larger than 0.043. All right, number 3, we're going to do electrolysis. We start with aluminum oxide, and then we end with aluminum. So we have to calculate the number of moles of electrons that must be transferred to generate 235 grams of aluminum. Let's first convert grams of aluminum into moles. Let's convert moles of aluminum into moles of electrons. So based on the charge, that would be 3 moles of electrons, since aluminum has a charge of +3. So correct answer for part A is 26.1 moles of electrons. Now as far as time needed to generate this amount of aluminum, let's take that number of moles of electrons and use the Faraday constant to go from moles of electrons to coulombs. 152 amps, that's 152 coulombs per second. So correct answer for part B is 1.66 times 10 to the 4 seconds. In part C, we have to use the ideal gas law. So we know that we have 235 grams of aluminum that's being produced. We can convert from moles of aluminum to moles of carbon dioxide using the 4:3 ratio between aluminum and carbon dioxide. We're going to plug that into the ideal gas law. So PV equals nRT, where N is the number of moles of CO2. We have the gas constant, 300 Kelvin and 1 atmosphere, and we get 161 liters of carbon dioxide gas produced under these conditions. When aluminum is placed in a concentrated solution of potassium hydroxide, we get the following reaction. Aluminum solid plus hydroxide ions plus water produces this aluminum OH4 minus 1 ion, this complex ion. It also produces hydrogen gas. To get the cell potential for this reaction, we have to reverse the first half reaction and multiply it by 2 to get the AlOH4 on the right with a coefficient of 2. we have to multiply this half reaction by 3 to get the electrons to cancel out and get 3 moles of hydrogen on the right. So reversing the first reaction gives us a positive 2.35. Doubling it does not change the voltage. The second reaction multiplied by 3, we still have a voltage of negative 0.83. Again, the electrons cancel out, and we have an overall cell potential of 1.52 volts for this reaction. To then take this information and calculate delta G, we'll use the equation involving delta G and the cell potential. The number of electrons is 6. We have the Faraday constant and the voltage 1.52. And rounded off to 3 significant figures, we have negative 880 kilojoules per mole of reaction. All right, well, that represents the end of the Chapter 20 practice quiz. I hope those answers and explanations were helpful to you. Thanks for watching, and good luck studying.